Hello and welcome to the fourth lecture on the Standard Model of Particle Physics course, in which we are discussing the electroweak interactions basically. And in the previous lecture we actually talked about the Lorentz invariant phase space, and we discussed how exactly we should change the wave function normalization to make it Lorentz invariant, and with that we tried to see how exactly the n-body phase space that can be redefined. And now with that we would like to evaluate the expression of what we call the decay width of a particle. We know in particle physics most of the particles are unstable. They basically fragment into pieces and produces some other final states. So we will take one example and evaluate the decay width associated with that using what we call the Fermi's golden rule, which is the transition probability from state I to state F. Okay. So with that, let's get started and see what we can do. All right. So you remember that we had an expression of the phase space measure which was actually dq pi by 2 pi whole cube in a non-relativistic cases. So why this factor of 2 pi cube was coming in the denominator? This was basically coming because of the fact that each state occupies a volume in the momentum state. Okay? So that's precisely why you have to actually divide by those volume in order to find how many number of states are there in between momentum pi to pi plus dpi. So therefore the integral measure is dq pi by 2 pi whole cube, but then we said that when we include the wave function normalization, instead of saying that psi star psi is equal to 1, we introduce this psi star psi is equal to 2e. So with this introduction of what we called the relativistic normalization of the wave function with a factor of 2e, then we said that the transition matrix element also rescales to the transition matrix element in the non-relativistic case, and that is actually by the factors of this 2e1, 2e2, 2e8, 2eb etc. whole to the power half. Once we include it in the expression of the Fermi's golden rule, and instead of this non-relativistic expressions of T fi squared, we can use this relativistic expression for the matrix element or Lorentz invariant expression for the matrix element. Then essentially we get this factors of 1 by 2 Ea out, and then this phase space parts become dq p1 by 2 pi whole cube into 2e1 and dq p2 by 2 pi whole cube into 2e2 for the case when we are considering A is going to 1 plus 2. In a sense, therefore, we say that the phase space integrals are now changing from dq pi by 2 pi whole cube to dq pi by 2 pi whole cube into 2ei. So there is this additional factor of 1 by 2 ei which is actually coming because of this change on the normalization condition. Now the question that we are going to evaluate is that is this factor of dq p by e is Lorentz invariant? Can we explicitly calculate and see whether this is really true? The answer is yes, we can do that. So what is dq p prime? dq p prime is dpx prime, dpy prime, dpz prime. Now if I want to rewrite it in terms of the S frame or the frame which is not moving, so then we can say that this is dpx dpy into dpz prime by dpz into dpz. Now why did I write it in this particular way? Because I am assuming that the motion is actually happening along the z direction. Okay? So therefore dpx prime is equal to dpx, dpy prime is equal to dpy, but dpz prime is related to dpz by this factor, that dpz prime dpz into dpz. So therefore this transmits into something like the old measure dqp into this factor of dpz prime by dpz. Now how this transformation occurs? So you remember we wrote this Lorentz transformation rules for one frame which is actually moving with a relativistic speed with respect to the other. And if I kind of borrow that same analogy to say that now x prime and x relation is related to Pz prime and Pz relation, because the motion is along the z direction we are assuming. So, therefore, this will be simply Pz prime equal to gamma into Pz minus beta E. So, here you know what I am going to do, that I am actually replacing the x by Pz and I am also replacing the t by E, because in the space time system we have the 4 space time components as like t, x, y, z, and here the 4 momenta construction is essentially the time component is energy and the spatial components are px, py and pz. So, therefore, this is the analogy with which we are now writing the transformation of pz prime to pz by this factor, like pz prime equal to gamma into pz minus beta E. What was gamma? Gamma was 1 by square root of 1 minus beta square. What is beta? Beta is actually V by C. In C equal to 1, this beta is equal to essentially V. Now, what happens to E prime? E prime is essentially T prime. So, x is Pz, x prime is Pz prime and T prime is essentially E prime, right. So, E prime will be what? It will be gamma into E minus beta Pz, okay. Now, we are actually able to calculate all these derivatives. So, dpz prime we can write that as del pz prime del pz dpz and del pz prime del E del pz dpz, right, and it does not depend on px and py, it is independent of that. So, therefore, there are no factors associated with them. Now, let us see what is del pz by del pz prime by del pz. So, this factor we have to first calculate. Can you tell me? So, this is very easy, del pz prime by del pz is nothing but gamma, that is apparent from the previous relation. Now, what is del pz prime by del E? This factor that we actually wrote. So, this is also straightforward, this is nothing but minus gamma beta, correct. Now, there is another factor that we have to calculate, which is del E del pz. Now, following this relation that E square equal to px square plus py square plus pz square, I can also write, you know, E square equal to p square plus m square, I must write the m square also, and so therefore, the del E del pz will be what? This will be simply pz by E. Now, if I borrow all these factors which I calculated into the expression above, what we actually get is that dpz prime is gamma dpz minus gamma beta into pz by E into dpz. So, in a sense, now we are ready to calculate this factor dpz prime by dpz, and this is essentially gamma minus gamma beta pz by E. Now, you can take the gamma by E factor here outside, and then what you are left with, this will be essentially E minus beta pz. Now, look into this expression, this gamma into E minus beta pz, that is nothing but E prime. So, this expression becomes E prime by E. So, dpz prime by dpz is nothing but E prime by E, or you can say dpz prime by E prime is dpz by E. So, this brings you to this very important conclusion that dqp prime by E prime, which is essentially dpx prime, dpy prime, dpz prime by E prime, because dpx prime and dpy prime remains unchanged because the motion does not affect them. What remains is that dpz prime by E prime, but in the previous expression we have already evaluated that this dpz prime by E prime is nothing but dpz by E. So, therefore, dqp prime by E prime is dqp by E. That basically means that this kind of a measure, the way that we have defined, is manifestly Lorentz invariant. This is invariant under Lorentz transformation. This is invariant under Lorentz transformation. So, now finally, we would like to once again get back to the expression of the decay width that we actually computed. So, we said that for the process A going to 1 to 2, how exactly we can write the decay width? The decay width will have a factor of 2 pi whole to the power 4 by 2 Ea, where Ea correspond to the energy of the initial state particle A, and then I have the Lorentz invariant matrix element square, which I am calling Ma phi square, and then I have the factors of the delta functions. There are two delta functions, one which makes sure that the energy of the process is conserved, Ea minus E1 minus E2, and the next factor is essentially the momentum factor del cube of, this is a 3 momentum, Pa minus P1 minus P2, and what remains are those Lorentz invariant phase space part. So, which is d cube P1 by 2 pi whole cubed into 2 E1 into d cube P2 by 2 pi whole cube into 2 E2. All right. So, this is the expression that we have. So, therefore, what we are trying to say that the Lorentz invariant phase space factor is essentially, sometimes people write it as d of LIPS. This is actually I equal to 1 to n d cube Py by 2 pi whole cube into 2 Ei. There is one question which still remains unanswered till now. Why this factor of 2 Ei? This factor of 2 was not very clear from the way that we actually devised this. We argued somehow that the wave function normalization must be proportional to the energy E, so that the enhancement in that factor takes into account the contraction in the volume. So, this is the way that we argued. However, why this factor 2E which actually comes, the factor of 2E, this actually propagates from this relation of so called non-relativistic transition matrix element to the Lorentz invariant matrix element square and so on and so forth. And then we actually explicitly demonstrated that d cube P by E factor is actually Lorentz invariant, but the factor of 2 is still not explained quite nicely. But we will show you now through this exercise that there is a nice reason that why this factor of 1 by 2 Ei is rather coming. And this is because of the fact that 1 by 2 Ei is nothing but the integral of a delta function which looks like Ei square minus Pi square minus Mi square integrated over dEi. So, once again let me make this statement once again, the integral of the delta function of Ei square minus Pi square minus Mi square integrated over dEi is nothing but 1 by 2 Ei. Now, how does it come? This comes from the fact, first of all, we remember that when we integrate fx with a delta function of x minus a dx, this gives you the value of the function at a, right? This is the first thing. Now, this is one of the definitions of the delta function basically. The other part which is important is that delta of fx, where the function sits within the delta function itself, then we can say that this can be evaluated as df dx whole to the power minus 1 evaluated at x equal to 0 into delta of x minus x naught. Now, this is something that I would like you to derive back home, or we can do it as a tutorial exercise. Okay? So, this is something that we have to do. Now, let us get back to this expression which I wrote above, that the integral of delta Ei square minus Pi square minus Mi square dEi. So, using this rule, what we can say that delta of Ei square minus Pi square minus Mi square should be equal to df dx evaluated at x equal to x naught. You remember? So, what is this? This is del del Ei of Ei square minus Pi square minus Mi square, right? So, this is the df dx whole to the power minus 1 evaluated at x equal to x naught. What is that x equal to x naught? X equal to x naught is the one where the delta function peaks, right? And that is basically Ei is equal to square root of Pi square plus Mi square, or rather this function that derivative has to be evaluated at a point where EI is equal to square root of Pi square plus Mi square. Now, if you take this derivative del del EI of EI square minus Pi square minus Mi square, what it is going to give you? This is going to simply give you 2 EI. Now, the inverse of that has to be taken. So, this is actually 1 by 2 EI, and this EI is evaluated at square root of Pi square plus Mi square. Now, what does it mean? Now, once again get back to the expression of this decay width that we calculated, gamma Fi for n body final state, say for example. So, we have the relativistic expression or whatever that you call, that will be pi of I equal to 1 to n d cube Pi by 2 pi whole cube into 2 EI, and now that one we are writing that 1 by 2 EI factor using this previous expression. I am saying that this is now an integral of dEI. Of course, this within this factor of pi of I equal to 1 to n, we have this d cube Pi by 2 pi whole cube. 1 by 2 EI, this is replaced by basically this delta function, delta of EI square minus Pi square minus Mi square, into dEI. So, in a sense, E square minus P square, that is what? That is, you can say that this is nothing but the 4 momentum square, Pi square. So, this you can say that this is the delta of Pi square minus Mi square, and you now see that this d cube Pi conspires with the dEI to give you a 4 momentum integral. This is turning out to be a beautiful expression, because although we said that d cube P by E is Lorentz invariant, but in principle the way that we have defined, we had a bit of a pinch of salt in our mind that how come this measure is written in terms of the 3 momenta, because ideally we should think that this should, if it is really Lorentz invariant, then this should be actually, the measure should be in terms of the 4 momenta, not in terms of 3 momenta. Now, that factor of 1 by 2i which was actually sitting in that expression is helping you to rewrite this expression in terms of 4 momenta, and that is manifestly Lorentz invariant, right. So, therefore, what you can say that this expression is turning out to be pi of I equal to 1 to n 2 pi whole to the power minus 3 delta of Pi square minus Mi square, where this Pi is not the 3 momenta, but rather the 4 momenta associated with all the I number of final states, and integrated over the measure of d4 Pi. Okay? So, together for gamma of Fi a going to 1 to 2, we can say that this expression turns out to be 2 pi whole to the power 4 by 2 Ea Mfi square into 2 pi whole to the power minus 6 into, now you see that these two functions, delta of Ea minus E1 minus E2 and delta cube of Pa minus P1 minus P2, this is actually a 4 delta, right. This you can say that this is nothing but delta 4 of Pa minus P1 minus P2, right. So, let us put that back, and we already argued that this is nothing but now the delta function involving where we were. So, this is the delta 4 of Pa minus P1 minus P2, and the measures d cube P1 by 2 pi whole cube to P1 is turning into delta of P1 square minus M1 square into d4 P1, and the other part is delta of P2 square minus M2 square d4 P2. Now, this expression looks absolutely beautiful, and this basically tells you that what are the things that you actually have. The integral is now extended to all values of the energy and the momenta for each of the final states, right? Because I have essentially the delta functions to ensure the contribution from the energy momentum compatible with the energy momentum conservation. So, the delta functions will do that. I will do integrate over all possible values of the energy and momentum, and this is now turning into a measure with respect to the 4 momentum instead of the 3 momentum. And finally, this delta 4 of Pa minus P1 minus P2 is basically telling us the energy momentum conservation of the initial and final state particles. That is one thing. And secondly, there is another, these 2 delta functions P1 square minus M1 square and delta of P2 square minus M2 square basically ensures Einstein's energy momentum relation for each of these final state particles that are produced, like Pi square is equal to Mi square, correct? So, with this actually we arrive to this nice expression of the decay width for A going to 1 plus 2. Now, you can extend this to actually calculate for 3 body decay, 4 body decay, whatever that you want. Okay. So, these are some of the exercises that we are going to do. We are not going to worry about the matrix element square for the time being. Once we have kind of ensured that this is a Lorentz invariant matrix element square, but the phase space part we have nicely arranged, and now this, at least the phase space part, looks nicely Lorentz invariant, right, because it involves the measures in terms of 4 momenta and so on and so forth, and energy momentum conservation is nicely imposed. We can also calculate the detail of the 2 body decay in what we call the center of mass frame. Now, what is the center of mass frame? When we have a decaying particle, we say if that particle is decaying from rest, suppose we have this A particle which is decaying from the rest. So, if I ensure that Pa, the 3 momenta associated with the particle is 0, then I call that frame to be center of mass frame for the decay. We will once again come back to this idea of center of mass frame from the cross section, but that will be in the next lecture. So, if Pa is equal to 0, that is 3 momenta associated with the decaying particle is 0, that basically means the energy of that particle is basically Ea is equal to Ma. So, this denotes the particle at rest. So, now if I kind of rewrite this expression which we have derived above, so where I am actually not using the delta function notation, rather the 3 momentum notation, because it is easier to use that when I am actually doing the delta function integration, which I am going to do in a moment. So, therefore, I am using that relation 2 pi whole to the power 4 by 2 Ea into integral of Ma phi square into delta of Ea minus E1 minus E2 into delta cube of Pa minus P1 minus P2, and these are the Lorentz invariant phase space parts, which is like d cube P1 by 2 pi whole cube into 1 by 2 E1 into d cube P2 by 2 pi whole cube into 1 by 2 E2. Now, if I sort of use further that this Ea is equal to Ma and arrange this 2 pi whole cube nicely, then this expression turns out to be the factor of 1 by 8 pi square Ma mod of Ma phi square. This factor delta, this Ea becomes Ma. So, this is delta of Ma minus E1 minus E2. Remember that Pa is equal to 0. So, the second delta function that we actually have, delta cube of Pa minus P1 minus P2, turns out to be delta cube of P1 plus P2, and that is the case. That is P1 plus P2 equal to 0 is the case. That is what is ensured, and this phase space parts, once we have kind of taken out the factors of 2 pi, reduces to d cube P1 by 2 E1 and d cube P2 by 2 E2. Now, what does this integral d cube P1 plus P2 d cube P2 provide? This basically says that I impose P1 is equal to minus P2 or P1 plus P2 equal to 0, right. So, I can perform one of these integrations of d cube P2, say for example, and reduce that integral or the transition matrix element into something like 1 by 8 pi square Ma mod of Ma phi square 1 by 4 E1 E2, remaining delta function is just this one, delta of Ma minus E1 minus E2 d cube P1. Okay? And here I must remember that E2 square is equal to M2 square plus P2 square, and just because P2 is equal to minus P1, so this E2 square will be M2 square plus P2 square plus M2 square is equal to M2 square plus P1 square. Now, what is d cube P1? d cube P1 you can also write as P1 square d P1 d omega, and so that therefore writing that we get this expression that gamma fi is equal to 1 by 8 pi square ma integral of mod ma phi square. This delta function delta of ma minus E1 is square root of m1 square plus p1 square, E2 is square root of m2 square plus p2 square, plus using p2 equal to minus p1 I can write m2 square plus p1 square, and this measure d cube p1 is p1 square dp1 d omega by 4 E1 E2, that factor is there. So, I can say that this expression looks like something like mod ma phi square integral gp1 delta of fp1 dp1 into d omega, where this gp1 is these other factors like p1 square by 4 E1 E2. Okay. So, the gp1 is nothing but p1 square by 4 E1 E2. So, what is fp1? fp1 is nothing but this function which is inside the delta function, which is ma minus square root of m1 square plus p1 square minus square root of m2 square plus p2 square, which is evaluated at p1. Using the same formula which we talked about before, this delta function, we can say that this function, this integral mod of ma for I square gp1 delta of fp1 dp1, this will be simply mod of ma phi square gp star, the derivative of this function with respect to p1 evaluated at p star and taken an inverse, so that f of p star is equal to 0. So, this is precisely what we have to do. Now, let us look into this expression of f of p1 and take the derivative df dp1. So, this derivative will be p1 by square root of m square plus p1 square, which you can say E1, plus p1 by m2 square plus p1 square whole to the power half, which is actually E2. So, if you kind of arrange this p1 by E1 plus p1 by E2, then this can be arranged as p1 into E1 plus E2 by E1 E2. So, p1 into 1 by E1 plus 1 by E2, which is E1 plus E2 by E1 E2. Now, let us get back to this expression like gp star df dp1 evaluated at p star whole to the power minus 1. What will happen to this? That this gp star is p star square by 4 E1 E2, and df dp1 is, if you take the inverse of it at p star, then this becomes E1 E2 by E1 plus E2 into 1 by p star, where p1 is evaluated at p star. So, therefore, this E1 E2 cancel, one of this p star cancels, and what we are left with, that this expression becomes p star by 4 ma, where I have also used the fact that E1 plus E2 is actually ma from the delta function. Okay. Now, let us get back to this point, that this integral, therefore, mod of ma phi square delta of ma minus E1 minus E2 delta cube of P1 plus P2, this measure d cube P1 by 2 E1 d cube P2 by 2 E2 simply turns into a beautiful expression like P star by 4 ma mod of ma phi square. Now, these momentum integrals are all done. What I am left with is only the integration over the solid angle d omega. So, this expression for gamma fi for the decay of A going to 1 to 2 in the center of mass frame, where the initial particle is actually at rest, turns out into something very nice and beautiful, that this is P star by 32 pi square ma square mod of ma phi square into d omega, which is the solid angle. Okay. So, this is the decay width of A in the what you call center of mass frame. Now, what is the P star? That is also something a question, and I am not going to go into the details, but you are going to do it in the tutorial exercise, and we can show that P star is the one where f of P star is equal to 0. Now, we know what is f of P, right. So, therefore, if you put this back, do a little bit of algebra, you can find that this P star at which this expression is evaluated is actually this one. Okay. Alright, so now it is important to note that there is a factor of 1 by 2 EA which is now turning into a factor of 1 by MA rather in the rest frame. This factor in the decay width, this is actually making us a very important point that the decay widths are not Lorentz invariant, because there is a factor of EA and this actually depends on which frame from which the decay happens. If you are happening it from the center of mass frame, which is this the one that exercise that we have done right now, then this EA becomes MA. If you are having a boost, then there is a value of PA and it is a different one. So therefore, you say that although we kind of shaked and baked this expression for the phase space very nicely to be Lorentz invariant, but this full expression of the decay width is not Lorentz invariant, just because of the fact that there is a initial state and the factor of initial energy of this particle from which it is decaying to this two particle 1 and 2, that depends on the reference frame. If you have the center of mass frame, it only depends on the mass of it, but if it is boosted, then it has a factor of EA in it. Those are not Lorentz invariant. So although the rest of the expression we could make it Lorentz invariant, but the full expression of the decay width at least is not Lorentz invariant. So this is an interesting point. You know, a particle can decay to different final states. We will take many examples of such kind, and in that case what we can say that the decay width should be sum over all, the total decay width of that particle will be sum over all these possible decay final states, and the lifetime is essentially the inverse of the decay width, right. So this is something that we all know, and we also define something called a branching ratio, and the branching ratio to a specific final state is stated in this specific way that you calculate the decay width to that specific final state and then divide by the total decay width of that particle. For example, like tau particle, you remember we introduced the tau particle that can decay into two different final states. How this decay is possible, we are going to talk about that later, but tau can decay to both electron antineutrino plus tau neutrino, and it can also decay to a muon antineutrino and a tau neutrino. And if you calculate that these decay branching ratios are almost half and half, but it is not that the case is not always like that. So we will consider the decay width of all these other particles. So there are very few particles which are stable. Most of the particle actually decays. The Higgs decays, the Z boson decays, all these particles which are actually heavier, which actually decays, and we will calculate the branching ratio. We will calculate the decay width to a specific final state, divide by the total decay width, and we get a branching ratio to that specific final state. Okay, so with that we actually finished today's lecture, and we will actually talk about the cross sections in the next one. Okay, stay tuned. Thank you so much.